SwayamPrabha. Digital India. Educated India.
Welcome again to this course on Introduction to Soft Matter. We were discussing last time two important phenomena that we had discovered, which is the creep phenomena and the stress relaxation phenomena. So, let us just quickly go back to that. So, what we had seen, and this is a combined graph of all of them, all the three important behaviors that we had discussed. So, we found that when you apply a known amount of stress to a system, the two classical materials, the solid and the classical fluid, they behave differently, and the viscoelastic response is somewhere in between the two. And we had said that this particular curve, we are going to denote this as J T, sigma. So, the creep function is a function of two important variables, time and the stress applied. In here you can even write it as sigma naught, and in general terms you can write it sigma. So, this is the creep, and in the next one, the stress relaxation phenomena, we introduced ourselves to the other phenomena where we said we are applying a known amount of strain and then the stress decreases over time. So, this curve was given the name G, or was denoted as G T comma epsilon. So, once again it shows you that it is a function of two very important variables, time and the known amount of strain imposed. So, we are going to look at this in a little bit of more detail. This one more thing. So, to make sure the system is so the strain here is being applied at time t equal to 0. So, what we are going to do is we are going to define this function such that we know that this function is equal to 0 for t less than 0. So, this function becomes well defined, and similarly for the other case we are going to say that, or impose the condition that this function be 0 for times less than 0, assuming that obviously all the experiments are beginning at 0. So, this is the origin. So, then we have a continuous function that we will be able to integrate and perform other important calculations with. So, what we had started off with were these different tests, right. We have finished of the first discussion of the first three, and now we want to discuss the fourth one, which is the effect of different histories. So, let us do that. So, here we want to now have a discussion on effect various histories. Before we do that, let us have a just quick recap of what we have for an elastic solid. We did a number of different strain control and the stress control tests, and what we found out that the generic graph, if you were to plot the stress versus strain, looks something like this, where you have an initial portion and then now this graph does not depend on the history by which you arrived at this situation, which means it does not matter how you did the experiment or how you imposed what values of stresses that you chose, or what values of the in a strain control test, what values of strain that you chose, you will always end up with this graph. but that does not happen anymore for a viscoelastic fluid or viscoelastic material. So, this was your just a generic response of a solid body. So, now let us, if we want to try and understand that, what we should do is, let us have a condition where you are applying a known amount of stress. This is time. Okay, so, this is time, this is stress, this function ends here, and then you have, you can either do it this way or you go through a different path, different paths to arrive there. So, let us call this path 1, this is path 2, this is path 3. What we see when we do these experiments is you are going to be recording the strain with time here, and what you see is that in this case, so let us say this is the response to path 1. The response to path 2 can end up at a different location, and here your path 3 can end up at a different location altogether. Please note the consequence of this graph. This is, let us say you get it from an experiment. So, here at a certain time where you have ended or some t dash, all the 3 experiments or the 3 paths have the same stress, but on this curve you do not have that. You will end up with different values of strain at these different times. So, when you create a merged, when you create a graph of stress versus strain, what you find is the responses are no longer unique. In the first path, this will be, this is what it might look like. The second path, and then this is your third path. So, for viscoelastic materials, you no longer have unique sigma epsilon relationships. And this is where history dependence comes in. So, for you to know the response state of a viscoelastic material, you must know now the path by which it had come there, because it is no longer enough for you to provide, for anybody else to provide an instantaneous value and then demand an instant, the value of the instant of the response at that time, because the response at that at time t depends now on the previous states. And if you remember, in one of the first lectures we were discussing how time becomes an explicit parameter, but for classical viscous solids and classical elastic material solids, sorry, classical viscous fluids and classical elastic solids, though time is an important parameter and that is how you are conducting the experiment, it hides somewhere. Although it should have been a parameter that was there, but the time variable disappears, right, because you are only relating instantaneous response to the instantaneous value of the stress, but no longer will that be true, and this is exactly where the history dependence becomes important. So, this is where viscoelasticity deviates strongly from your what you might have studied in classical viscous fluid mechanics and solid mechanics. Okay. So, we have discussed 4 tests, right, that leaves us with energy dissipation and effect of sinusoidal oscillations. So, since we have always been discussing, so let us, so this is the 5th test, we can discuss that. So, energy dissipation. Now, the moment we say energy dissipation, we have to recall what we had said for the 2 other classical cases. In the case of the solid body, all of the energy is stored, whereas for the fluid all of it is lost. But here obviously now that we have started to realize that this is somewhere in between, the response will also be somewhere in between. So, some of the energy may remain stored while the rest is lost or dissipated. Dissipated to where? To the surroundings or within itself, dissipated as heat. Brings us to the 6th and the final test, sinusoidal oscillations. So, if we apply epsilon equal to, let me this epsilon, if you make in an experiment the strain a function of time, the sinusoidal function of time, and then you measure the state of stress, this now will have an amplitude, and I will write both of them in a second. So, I will first write the sine portion, the sinusoidally varying portion. We had seen that for an elastic body the two are supposed to remain in phase, whereas for a viscous fluid there was going to be pi by 2 difference, but now you are not going to have that. Instead, you are going to have some other difference where delta is not pi by 2, it is some other value. And here in the numerator, in the amplitude part, you are again going to have a constant part and something else that depends upon omega, the imposed frequency. Right. So, out of these 6 tests, in our course we will see that the first one is very important, because this gave rise to the phenomena of creep, and we realize that we have to understand. So, associated with that we gave this symbol or the function j. And then the strain control test is also very important because this is your stress relaxation. This gave rise to that phenomena. The other three are also very important. We will see how this plays a role at a slightly later stage. And for this particular introductory course, we will not worry too much about test 5 and 6 so much, but they are also very important. In a more advanced course, you will learn in more detail, but for the sake of this particular course, we will be focusing on these two important phenomena. So, before we go into a little bit more depth about this, we will just quickly come back to the stress relaxation phenomena, because this serves to illustrate an important point, and that is now G. So, I can create an artificial modulus So, this function g can be used to define moduli, the various. And in polymer engineering, a lot of people use the function g at t equal to 0 to given epsilon divided by that epsilon, and this is also called the initial modulus. Or you can even define another modulus where this t is tending to infinity, and this is also called equilibrium modulus. So, some people use this and quite a bit. For example, in polymer engineering they use this, and the important point here. So, we will do this in a little bit more rigorous fashion in a second, but the important point is that these two moduli can be different by even orders of magnitude. So, unlike the case of this the classical elastic solid, where you could attach one modulus and that one modulus was enough to define the behavior of the material, that is no longer going to be true. So, you are having the modulus itself is now a function of time. The purpose of this was to illustrate the fact that this j t comma sigma and g t comma epsilon can be used to characterize material properties. Material properties. So, basically the creep and the stress relaxation tests can be used. So, the question that we want to ask is, so the question, we have a question right now, and the question is, can creep and stress relaxation phenomena be used to define material properties? This is our question. So, we are going to look into this in a lot of detail now. So, let us consider, let us say that you are now visiting the lab. Okay. You have gone into the lab and you have the first test you want to do, because you have learned that there is a list of tests, and the first test you are saying that what I will do is I will impose a known amount of stress to the system and I will see what the response is. But what amount of stress? If you go, you might decide on a one value. So, let us say student 1 goes, he decides on a value of sigma 1, he does the experiment with that. Then we send somebody else, that person goes, he does the experiment again, but this time he chooses arbitrarily some other value. And so, a third student goes and he decides to conduct the experiment at a third different level of stress. So, if you were to put together all the results, what we will see is there will be so the three people will see three different graphs. So, the first person records J t comma sigma 1, meticulously records this. The second person has meticulously recorded the response at the other level of stress, and so has the third person. Now, all of these graphs actually represent material properties, so they are representative of the material behavior. So, now you have all a family of curves which now represent material behavior. But what happens? So, this was the stress relaxation test, the creep test. What happens for the other test? If you were, so if somebody went and if a set of students decided to do the stress relaxation test instead in one of their days at the lab, then what would they find? They would apply, sorry, this is strain. They would apply value of strain. So, the first guy goes, does an experiment, imposes one amount of strain, epsilon 1. So, he gets a corresponding graph. We will call this G t comma epsilon 1. The second guy goes and he chooses a different value, and again he gets a different curve, and so does the third person. So, now once again in the stress relaxation experiment, you once again end up with a family of curves. So, this is a problem, right? Well, I mean, it is not so really a problem. Maybe a material is so complicated that you cannot define it with one more graph anymore, like you were able to do in the case of the stress strain curve for a solid like mild steel, for example. But here you have a set of curves, so you cannot get away with it. But there will be some, perhaps there is some condition under which you can simplify this. So, it does turn out that there is a condition which is called the linearity of scaling, under which you can make some simplifications, and we will see that in the next class how linearity of scaling helps us define material properties from the creep relaxation test and the creep test and the stress relaxation test. Okay. So, yeah, we will end this class here.